Time to begin. And today we actually are going to start with doing some quantum physics, actually, doing calculations, doing the things to show, to try to find information. And we always start with the particle in a box because, it's a simple problem and it's illustrative. But before we even do that, have to talk a little bit about the Schrodinger equation, which I just noticed I have a problem with. Can you see the error in the equation on the screen? When you see it, you'll see it's really significant. There's something amiss with this term right here.
Am I missing an I?
Not the I. It's more significant than missing an I.
Oh, the psi.
Yeah, it's missing the psi. It ain't right without the psi. I can't believe that I didn't notice that until class time. So this equation has two variables, time and position. So with two variables, of course, you have yourselves a reasonably tough problem. So the first thing we're going to do, and of course it's much worse if it's three-dimensional, what we're going to do first is to separate the variables to get it so we just have an equation of one variable. So we're going to separate this so we get one Schrodinger equation for time and a second time-independent Schrodinger equation. And then we're going to work with that time-independent Schrodinger equation for the immediate future. So the first step in doing that is to identify, I don't need to see myself. Boy, no. Now I just see you guys and I can see you better. And I'm hungry, dude. See, I couldn't tell I was eating even. So the first thing we're going to do is say, we can make the assumption that our wave function can be written as the product of one function of position and a separate function of time. So if we can take our wave function and make it the product of one function of position and one function of time, then we can put that into the Schrodinger equation. So we're going to have you can't tell the difference in my X and my T, can you? Better?
Yeah.
So there I've just made the substitution. Sorry, I just shrink it down though. Just made the substitution of our new set of two functions. Oh, Richard. I'm just trying to move this so it fits better. That's all I'm trying to do. That fits better. Okay. How does this help me at all? Here is how it helps me. This derivative with respect to time, notice it's a partial. Everything in that original Schrodinger equation was partial derivatives. So this partial derivative with respect to time, how does that affect psi of x? Does it? That's right. So I can rewrite this left side, bring out the psi of x, and then I have I h bar d dt of just phi of t. Now looking over here, by the way, something that you may or may not have noticed, I'm generally careless about this, uppercase versus lowercase. the full wave function was uppercase psi. The position portion of the wave function is lowercase psi. So it seems like I just substitute psi with psi times something, but it's uppercase versus lowercase having different meanings. And I noticed when I was looking at the homework solution for chapter 2, which I did post that this morning. I'm sorry it took me so long. I forgot it wasn't posted. I used lowercase size when I should have used uppercase size, and I did not want to go through and replace every single occurrence, so I didn't. Okay, so over here we have a similar relationship. This one's a derivative with respect to x. Oh, brother. And so that's not going to affect at all the phi or phi. No fo or fum options. So I'm going to bring that out. And then finally, the last one, my potential energy operators generally just a multiplicative thing, or a function of x. It's not a derivative, integral, or something that's going to change it. And so in that case, it's just completely unaffected. So I have so that's rewriting the equation. I used colors here to indicate the things that I had moved. And now the last step, the coup de grace, is to divide every term by my entire psi. That is the position-dependent part and the time-dependent part. Now we get ourselves into a cool situation. Let's cancel where we can. In the first term, come on, go away. First term, I can cancel the size because I have psi over psi. In the second one, I can cancel the phis. In the third one, I actually could cancel both, but I'm only going to cancel the phis because it's still a function of x. That's why I didn't worry about canceling the size. It's a function of x. But now I have a cool situation. I know this is bad for you looking at the slides later, but I'm going to erase the parts that I canceled. Now, if we look at that, the left side of the equation is a function of one variable. What's that one variable? T. Once again, that time was hard to read. So this is all a function of time. The right side is all a function of one variable, but that variable is x. How can I have a function of time equal to a function of position? There's only one way. The only way that works if this is equal to a constant. That's the only way it's going to work out. And so this gives us two separate Schrodinger equations. One that is E is equal to I h bar d dt phi of t all over phi of t, which of course we usually would rewrite as My pronunciation of phi, by the way, is probably different than everyone else you've heard, right? Most people say phi.
Most people I know say phi.
Oh, do they? Okay, well, good. When I was in graduate school, I had a Greek classmate, and we were talking about just solving a problem. She said, and this is, area is PR squared. It's like, P? It's pi. You're Greek. You should know that. And she's all, I forget you Americans pronounce it pi. The I sound should be E. And so PHI for phi, that should be E as well, according to that logic. That's why I pronounce it that way. Just so you know. But I still say psi instead of C because I learned psi a long time ago. Just so you understand the weirdness that goes on over here. So there's one of our equations. The other equation, there I wrote it out in the same way as it comes from what we had here. And then the simplified form that we use, or the normal form we use, ooh. I can't remember if it's an E or an A there. And if you want to know how to make that on your Windows keyboard, hold down Alt plus 0246 on the number pad. That's how you get that O umlaut. For this class, I have to type it a lot. Okay, so that's our time-independent Schrodinger equation. And up above, we have the time variation. Now, there is one more thing that technically comes into this. We introduce a quantum number, actually, when we do this separation. So we have a quantum number that's associated with, there could be energy state 1. It has to be E1 for both of them, or energy state 2 would have to be E2 for both of them. And so we have a quantum number here to associate since we did the splitting. So we have two variations of the Schrodinger equation now. Now remember, this is not going to be on the exam on Friday. This is going material that will come on the second exam. So you don't have to say, oh, I've got to know this for Friday. But when we talk about the Schrodinger equation, oftentimes we simply say Schrodinger equation. We don't say time dependent or time independent. And so you start to get fuzzy because what's the difference in the time dependent and time independent? Time independent has the EN there, whereas time dependent has IH bar DDT. And so they're so similar, it can be confusing. So I want to be really clear why there's a difference. It's because we've done a little work to separate out the time. So there's the two equations we just did. And now we're going to work on solving these equations. Now you guys are both in differential equations this semester, is that correct?
Right.
Have you learned to solve this equation yet? No?
Yes, that form.
Okay, well, the key to solving it is separation of variables. Surely you've heard that term, right?
Yeah.
So we have two variables here, time and our function phi. And so I need to have all the phis on one side and time on the other. The E is a constant. And so I take this and I simply separate it. So I'm going to have divide everything by phi, multiply everything by dt. And so what I'm left with is canceling of the dt's over here, canceling of the phis over here, and it's that's a phi. Now you look at this equation, and you have to remember that while calculus, a derivative is not technically a fraction, mathematically we treat them as fractions. And so what I did here was just treat it as a fraction, and now I have the left side of the equation is the only variable is phi, the right side of the equation, the only variable is time, and I can move on. Oh, I want to point out, I changed from partial derivatives to exact derivatives. The reason I did that is because there is no difference if you have a one variable problem. It's only if you have multiple variables that you have to keep the partials. So that's why I change it to exacts, so that you don't get confused. Say, I'm not sure where this step comes in. Just some math and I didn't. All right. So now we integrate both sides independently. So the left-hand side, if you integrate d phi over phi, that's going to give you, we still have the constant, so I keep the IH bar out there. On the right-hand side, integrate the E and you have, or E dt, that's constant, so it's just ET. Now, of course, I didn't worry about plus C's here. So to solve this for my function phi, I'm going to have to divide everything by IH bar, which gives me, I'm going to change color so it doesn't look like a continuation of the equation. Nobody likes to put 1 over I. So we put I, E over H bar, T, had to change it from a plus to a minus sign to accommodate the multiplying by I squares minus 1. Question, Chris? Go ahead.
Is there a reason why nobody likes the I and the, or 1 over I?
Well, I learned back as a kid that you should always have rational things in the denominator. If it's going to be irrational, it needs to be in the numerator. So that's probably why. That's my best answer. So now, of course, natural log, the inverse function of natural log is the exponential. So you just do the exponential of this is equal to exponential of that, or exponential of that. And if I wanted to be technical, I would have put E sub n's everywhere, because you have the different possible E values. So that is our time dependence. Is that normalized? How would we determine?
It doesn't have a constant out front, or you could integrate it if you wanted to over all space.
So let's check. Now, all space for time. This is a repeating function, right? And so we're just going to take over one cycle. See, what would the cycle be? That would be one cycle. Notice I have the complex conjugate times the original. That's the integral of 1. So that's going to give me something. It's going to give me that. Now I'd say, no, that probably doesn't look like it's normalized. Problem is, I swear it was supposed to be normalized. But I'm going to go on from here because I didn't even think about checking that one for normalization. We always just check the other one for normalization. This here, when we do normalization in space, this is in time. When we do normalization in space, the time one is going to disappear. It becomes the 1. And so the normal normalization calculation, integrating over all space, so here I'm making it clear that I'm using the full psi, is equal to integral of this psi star, phi star, this psi, phi. But those two combine to just give me 1 and disappear. So I do not need, in fact, I should not have an additional factor out here. Because if I did, then that would not be 1 for those two terms. Because one's the complex conjugate of the, or the exponents are complex, the phi star, phi multiplied together just gives you 1. And so there is no time dependence in this, and it's an integral over space. So that's why we don't worry about this. We don't try to force any normalization on this, because in our total wave function, as long as the spatial part is normalized, then we're going to have a normalized wave function, because the integral is actually not overall time, it's overall space. And in fact, we showed in one of the previous lectures that that normalization condition is going to remain constant over time, that it cannot become not normalized over time. Now let's go to the time portion. You'll see in a slide or two it says, spend all the rest of the class time working on this problem. I have more slides that I'm going to get to. I made that note so I wouldn't try to go on to another slide. So now we have the time-independent Schrodinger equation, which honestly, almost everything we're going to do from here on out is going to be using that time-independent Schrodinger equation. So pretty soon, if you're like me, you'll just say the Schrodinger equation and mean the time-independent one, because that's the one we're using. We're going to have more than one possible solution that we get, but they're time-independent solutions, so we call them stationary states. Stationary because they don't depend on time. So let's just get to it. Our complete wave function is going to be a linear combination of our spatial wave function and our temporal, our time wave function. The C is telling us basically what percent it's in each state. Think back to the Schrodinger cat problem. The Schrodinger cat problem, you had two states, which started with the radioactive nucleus. State 1 was the undecayed state. State 2 was the decayed state. And the C sub n is the constant that tells you what the probability is of being in state 1, probability of being in state 2. And for that problem, the C's vary with time. So that the probability of being in state 1 started as 1 and goes down to 0. The probability of being in state 2 started at 0 and goes back to 1. But the entire wave function has to remain constant with the probability of 1 for the wave function at all time. So linear combination, for that wave function, we could write it out simply because it was only 2 states. It would be C undecayed psi undecayed of x e to the minus I energy undecayed time over h bar plus C decayed psi decayed e to the minus I energy decayed time over h bar. And that would be the entire wave function then for the Schrodinger-Cat problem, which truly applies to the atom, but we have our measurement device as the cat, and so we apply the same quantum statistics to the cat, the idea being to illustrate how ridiculous it is to apply those requirements on the cat, that it has a certain number out here that says it's this percentage. If you do the C1 mod squared, that gives you the percentage it is in state 1. The C2 mod squared is the percentage in state 2. And so it says the cat is this percent in the fully alive state and this percent in the fully dead state. So that's why the Schrodinger cat problem is there. It's trying to make sense of what this can mean. And saying the cat is, 30% fully alive and 70% fully dead doesn't seem to make sense. That's why it was proposed. Okay, so now to the problem. Spend the rest of the class period solving the problem. Don't worry about the rest of those pages. So this is not technically real. You don't really have a particle in a box, but you can have particles in a finite well, and so it's reasonable facsimile to a real problem. So first, let's try to lay out what the problem means before we solve it. Because if you don't have what the problem means, you've only done an exercise in math, and then you're like, but how would this ever relate to real life? I don't know. It seems like quantum physics, we're just doing math. So what this is you have a potential energy. Usually we use, here it's V for potential energy, that is 0 if in the box. But it's infinite if outside of the box. And so I have written here a reasonable similar thing is a wire. The electron's energy doesn't vary as it moves through the wire's cross-section, but the electron can't leave the wire. It's stuck on the wire. Now, I said that's a reasonable facsimile because, of course, there's a certain probability, according to quantum physics, that the electron does leave the wire. But it's a reasonable starting point. The electron has to be on the wire, can't be outside of it. And so now we have this potential energy function. If the position is less than 0, notice 0 is one edge of the box. So if the position is less than 0, then the potential energy is infinite. If you have an infinite amount of energy, you could move it to outside of the box. But of course, by definition, you don't have an infinite amount of energy. And I'll use less than equal. If it's inside the box, the potential energy is 0. Now, that really only has to be a constant. It could be 5 joules. But if it's any constant, remember, potential energy has an arbitrary reference point for where 0 is. it makes perfect sense to me to set that reference point to 0 because it's an easier number to work with mathematically. And then we have if x is greater than L, the potential energy is back to infinity. So we've clearly defined the 3 regions, and now we're going to find a wave function in each of these 3 regions. So I'm going to name these region 1, region 2, and region 3 to make life easy. So in region 1, this doesn't take really large thinking power. Since I have psi multiplied by infinity, what's the only way to make this equation true?
Psi 0.
Yeah. So this has its only solution is the trivial solution. When I was taking differential equations, of course, every problem said you can't use the trivial solution. The trivial solution is psi of x equals 0. But in this case, that's the only one that works. So we're done. It's the only one that works. We don't have to find another one because there is no other one that works. Let's go to region 3. Need I say more? No, thank you. So psi in region 3 is also equal to 0. Now that's made our life a lot easier because we don't have to worry about going to infinity anywhere, x going to plus infinity, x going to minus infinity. So my psi is 0 outside of the box, which makes perfect sense because what's the probability that it's outside the box? If it's not going to be allowed outside, what's the probability it's outside? 0. But what is calculus or quantum mechanics, the calculation for the probability of being outside?
Psi mod squared.
Yeah. And so the probability of being outside has to be psi mod squared in the outside region. It's probably being outside 0. Psi mod squared better be 0 outside. So those there had to be true given our rule that it can't be outside the box because it would require an infinite amount of energy. So we've done 2 of the 3 regions. Feel satisfied? We haven't accomplished anything, right? We've only found a way to mathematically write what we knew. But we're able to tie in ideas like what the probability calculation is to help it make some sense in a real life situation. So now we go to region 3. Or region 3, region 2. Region 2 has v is equal to 0. So now my time-independent Schrodinger equation minus h bar squared over 2m d second psi dx squared plus 0 psi to be technical is equal to en psi. Well, the 0 is meaningless. Get rid of that. Now I have a second order linear differential equation. You have not solved those yet, is that correct? Okay, so I always assume my students haven't solved these yet, and I'm not teaching you differential equations. Even when you take differential equations, it'll be like explained once and then you'll memorize. Solution has the form of. Psi of x is equal to e to the bx. And so given that it has this form, then I say, okay, if the solution has that form, let's plug it into the equation and find what b has to be. So I put it into my equation. Battery must be getting low because the screen just got darker. Take the derivative. Let's do the derivative separately. What's that derivative? Well, this was the first derivative. And so, obviously, you were totally with me. And so I'm going to replace that second derivative with b squared e to the bx. Now, a little technicality. Usually I cancel stuff. I felt a little uncomfortable when we separated the Schrodinger equation because I canceled stuff. These functions could be zero. And so the better way to do it is to factor. So I'm going to bring this over here and then factor out the e to the bx. So I'll have 0 is equal to e to the bx times that. Now, there are two situations that can make this true. Situation number one would be if e to the bx is 0, which would require bx is equal to minus infinity. Well, if b is plus or minus infinity, in this region, my x's are all positive, right? Region 2, the x's are all 0 and positive. So if b is minus infinity, then except for x equals 0, b being minus infinity would work. But that gives us the trivial solution of 0 for everything where x is not 0. So that's not the one we consider the solution. So it's the other possibility that gives us our solution. Simple enough. Square root both sides to find b. And you guys are astute enough that you probably know exactly what to do, but if you didn't have much math, you'd be, uh-oh. So what's the problem that you would have if you had only a middle amount of math? Yeah, square root of -1. There is one mistake, by the way, in what I wrote. Can you see the one mistake in what I wrote? Anytime you do a square root, there are always two answers. You cannot forget that. I have two b's that will be correct. One with the plus sign and one with the minus sign. And as you said, we have the square root of -1, which we're astute enough to know that's just I. So now I found two values for b. I have b plus is equal to I square root of 2m e to the n over h bar squared, and b minus is equal to minus I square root of 2m e n over h bar squared. Let's make life easier. Right, that's just easier. So that means that I've defined we can't forget the meaning of our K. Right? If we do, we're kind of in trouble. So we can come back, because I had two solutions, I said the solution had this form. So now I can say my solution is more specifically a linear combination of the first one and the second one. Now I'm putting a box around this. We're far from done, but we have found a solution to our problem. And so oftentimes you think, hey, I'm done. I found a wave function. But there are certain rules for the wave function. What are those rules? Well, rule number one, we've already learned, is it has to be normalized. I'm going to apply that rule last here. So maybe I should call that rule number 3. The next rule, which I guess I'll call rule number 1, is that your wave function must be continuous. So wave function is continuous at both boundaries. So we have two boundaries, one at x equals 0 and one at x equals L. And we're going to say our wave function has to be continuous at both boundaries. So we come out here. This was technically our wave function in region 2. And so we're going to test our boundary conditions. That's not how you spell boundary. So that means psi in region 1 at x equals 0 must equal psi in region 2 at x equals 0. Work for you? So that means that I would have, what is psi in region 1 for any x? 0 equals a1 e to the 0 plus a2 e to the 0. Okay, so that's just equals a1 plus a2. So we have a1 plus a2 equals 0. Simple enough. Then we go to boundary 2, which is going from region 2 to region 3 at x equals L. What is psi 3 at all places? And so we're going to have A1. I'm going to put A2 equals minus A1. That's the result that we found from the first boundary condition. So I'm only going to have one variable for my constants now. A1 e to the ikl minus A1 e to the minus ikl equals 0. So that's giving me a second condition. This is actually good enough. When you look at this, you're like, you know, that's really kind of annoying. Having those exponentials, is there an easier way? And of course, there is an easier way. There's probably 3 or 4 ways to show this, but I'm just going to go with Euler's relation. You guys know Euler's relation? Not by name?
No.
I'm sorry, I asked you, do you know this? No. Do you know this? No. That's why we're taking the class, right? Okay, so that's Euler's relation. Other ways we could have gone with this, would use the definitions that cosine of phi is equal to e to the I phi plus e to the minus I phi all over 2, and sine of phi is equal to e to the I phi minus e to the minus I phi all over 2i. Either one of those, because we have the minus sign here, we'd immediately go to the sine term, or we could just plug in Euler's relation. So if we plug in Euler's relation, well, actually, I need to back up a step before I do this. I'm going to make my substitution here just so we can see that's the general wave equation now. After we did the first test, because of this relationship, if I apply Euler's relation, whoa. So there, the green is the second term, the red's the first term. Cosine of minus kx, cosine is symmetric about 0. It's an even function. And so that's exactly the same as making a plus sign there. So these here are the same. Sine of minus kx, that's anti-symmetric. It's an odd function. And so there I have to change the outside sign. So just using the rules of sine of minus kx is minus sine of kx, and cosine of minus kx is cosine of plus kx. Then this combines to give me which I could have also just taken this form here and said, look. That would have been the same substitution, right? Multiple ways of getting there. And so this could be more easily written as 2iA1 sine of kx equals 0. Well, this gives me something interesting because, of course, if k is 0, then that would be true, right? Because sine of 0 is 0. But if k is 0, then what do I have for my wave function? I have 0. Because sine of 0 would always be 0. It doesn't matter if sine of 0 times x, it's still 0. So we can't use that one, or we're going to have 0 for our wave function everywhere, which means the probability of the particle existing is 0. It doesn't exist in the box or out of the box. So we cannot have k equals 0. So then we have to say, what other values of k will make this true? So tell me, what other values of k would make sine of kx? Oh, I'm sorry, this is L because it was specific KL. What other values of KL would make this equal to 0? Sine of what is 0? You say pi? Okay. Pi or 2 pi or 3 pi or 4 pi. So in general, KL is some integer multiple of pi where n is equal to 1, 2, 3, etc. Any positive integer, not 0 because that would give us no wave function. So then we can solve this for k. K is n pi over L. We now have quantized values, only specific values of k. Well, conveniently enough, not only is my battery dead, so is our class time. So we will start next class period, well, on Monday, dealing with this result and continuing on. All right, so I talked to Dr. Hansen, and he will arrange for somebody to be there to proctor the exam on Friday. It's just a 1-hour exam. Remember the format. I'll have an equation sheet with it. All right, I'll see you guys later.
Sounds good.
Thank you.
Yep, bye.